Okay, geometry semester 1 in-class review, day 3. So we finished up day 2 here on this problem. We're going to skip over these and we'll start here with this one. Okay, we notice here we have an isosceles triangle. This triangle here is an isosceles triangle. So if this piece is 72, right across from the congruent sides are going to be your congruent angles. That's your isosceles triangle theorem. So 72 and 72. Okay, and then we know the three angles of a triangle add up to 180. So we can do 180 minus 72 minus 72. That's 144. So 180 minus 144 is going to be 36. So the third angle of this triangle is 36. Okay. And then we have a right angle here. This is a right angle. So we know these two angles add up to 90 degrees. So we can do 90 minus 36. Right, which is going to give us, 54? Right, so we know that this angle here is 54. Okay, and then we have another isosceles triangle. So we know the base angles here are congruent. Okay, so we know these two angles here are equal. So we can do 180 minus 54. That's going to give us 126. So we know these two angles are congruent and they add up to 126. So we can divide that by 2, and that's going to be 63. So these two angles here will be 63 and then 63. So x would be 63. Okay, pretty simple there, seeing as we've done it several times. Okay, and then you also have these here for additional practice if you want to do those. But let's go on to the proof here. All right, so you have statements and reasons. So statements and then reasons. Okay, it really should be segment AB is congruent to segment DB. So step 1 here is our givens. So segment AB is congruent to segment DB. Okay, and then angle ABC is congruent to angle DBC. So AB is congruent to DB. We can fill that in. And then angle ABC is congruent to angle DBC. Okay, that is our givens. All right, and we're trying to prove that these two triangles here, triangle ABC is congruent to triangle DBC. All right, we already have one pair of sides and one pair of angles. We can use the reflexive property here to show that BC is congruent to BC. So BC would be congruent to BC by the reflexive property. Okay. Okay, and now we know these two triangles are congruent by side, angle, side, right? So since we have two pair of sides that are congruent, and the included angle are congruent, there's only one size and shape for those two triangles. Those two triangles have to be the same size and shape, so we can say that they're congruent. So now we can conclude that triangle ABC is congruent to triangle DBC. Right, once we know that two pair of sides and the included angle are congruent, so we have two pair of corresponding sides and their included angles are congruent, we know there's only one size and shape for those triangles to be. They have to be the same size and shape. So they're congruent, side, angle, side. Okay, so this one was pretty easy. They just gave you two pieces, and then you needed to use the reflexive property for the third piece, and then recognize that you have side, angle, side. All right, the next one here are given. We are two things are given to us. Segment AC is congruent to segment BC, so we can fill that in. Okay, and then DBC is midpoint. I took out the article, but D is the midpoint of segment AB. Okay, so we can fill in AC is congruent to BC on our diagram, and then D is the midpoint of AB. Okay, let's use the midpoint. So again, they're not going to give us information that we're not going to use, so we're almost certainly going to use it. So if D is the midpoint of AB, that means D is in the middle of A and B. So that means AD here is going to be congruent to BD. So we can say segment AD is congruent to segment BD. And that is the definition of a midpoint. That's what a midpoint is. It splits it in half. It's the very middle. Definition of midpoint. Okay, the midpoint's in the middle, so AD is equal to BD. Okay, and then again, we can use the reflexive property here, right? So we can use the reflexive property. Okay, and that tells us CD is congruent to CD. CD in the left triangle, segment CD in the left triangle is congruent to segment CD in the right triangle. Okay, and then that allows us to say those triangles are congruent because now we have 3 pairs of sides that are congruent. And once we have 3 pairs of sides that are congruent, we know those triangles have to be the same size and shape. So we can say triangle ACD is congruent to triangle BCD by side, side, side. Okay, again, fairly easy, fairly straightforward, I think. Okay, and then here's some SAT questions from last year. Okay, we did not talk about dilations yet, so we're going to skip over dilations, right, and look at some of these transformation questions here. Okay. I think there's 5 transformation or points worth of transformation on the final. So it's the smallest piece, and I think they're fairly simple questions. Right, so write a description of the rule x, y, right, the coordinate x, y, goes to, or is transformed to, translated to, x plus 10, y plus 8. So this means we're going to the right 10, right? This is our horizontal shift. So we're going to the right 10, and we're going up 8. So we're looking for 10 units to the right and 8 units up. So that's definitely going to be A. Right? So it's not going to be this one, not going to be this one, not going to be D. I missed the cross out though. Okay, we're going right 10 and up 8. If it was negative, it'd be down left 10. If this was negative, it'd be down 8. Okay, let's write a rule going from ABC to A prime, B prime, C prime. Okay, so X comma Y. Okay, our horizontal shift here, we're going from ABC to A prime, B prime, C prime. So we're going from A to A prime. So we need to go to the left, 1, 2, 3, 4. So since we're going to the left, that's going to be X minus 4. Okay, and then we're going up 1. So we're going minus 4 and then plus 1. So Y plus 1. Okay, and you could have picked any of these, right? We're going left 4, right? And then we're going up 1. Right, C here, we're going left 4, and we're going plus 1. Okay, so everything's going left 4, up 1. So here's our rule. Right, and remember, we could have also written it as a vector, negative 4, 1. That also works if we write it as a vector. We're going this way. Okay. So point A, negative 2, negative 10, is reflected over the x-axis, right? The coordinates of A prime. So if we reflect over the x-axis, that is our horizontal axis, we're going to be reflecting it up and down. So your x value stays the same, but you're going to change the value of your y. So negative 2 should stay the same, but it should become positive 10. Okay, and if we wanted a diagram of this, right, negative 2, negative 10 would be somewhere here. Right, so A prime would be up here. Right, so you have negative 2, negative 10. Right, you're flipping it up, so this is staying negative 2, but now becoming positive 10. Right, this is your x axis. Okay. All right, point D, 2, 4, is rotated 180 degrees around the origin. What are the coordinates of D? Well, we know the rule for rotating 180. If I Z here, right? Right, we're rotating 180 degrees around the origin. Right, right. We're rotating x comma y. Right, that's going to go to y comma x. Right, so we're simply going to be switching the x and the y. So 2, 4. I'm sorry, negative x, negative y. I don't know what I'm thinking here. Does it become negative x, negative y? So you're simply switching the sign. So 2, 4 becomes 2, negative 4. Okay. Right, and again, if we wanted to look at that, 2, 4 would be up here. Right, so this would be D. And then, right, 2, 4. We go 180. We're going to be down here. That's going to be D prime. And so it's going to be negative 2, negative 4. Okay. All right, which of the following transformations does not result in congruent figures? We didn't really talk about this, but it'd be dilations. These are the ones we talked about, right? These are all rigid transformations, right? Rigid transformations. Okay, which means they don't change their size or shape. They're rigid. So those are the ones that are congruent, the ones we talked about. Rotation, reflection, translation. We'll talk about dilations when we do similar figures. Okay, which transformation shows the image is similar to the pre-image? Again, this is going to be a dilation. Don't even worry about these two questions, though. All right, we'll get to that when we talk about similar figures. Okay. All right, which set of coordinates will provide the vertices of the translation of x, y, z 2 units to the left? So if we go 2 units to the left, x here is at negative 1, 1. So 1, 2, it's going to be at negative 3, 1. So we can eliminate A and C. Okay, z here, if we go to the left, we're going to be at 0, negative 2. So it's going to be B. Okay, and we could put y prime here as well, 2 to the left. All right, and we can connect these. We're simply moving 2 to the left, so it's going to be B. X prime, y prime, and z prime. Okay, and then we got a couple more here. So if this triangle is reflected over the y-axis, what would be the coordinates of K? So K prime. So K right now is 6, 6. Right? If we reflect over the y-axis, that's our horizontal axis here. Okay, our rule for reflecting over the y-axis, right, is our, we're flipping it left and right. So your y value is staying the same, and your x value is what's changing. So we're going to take the opposite for your x, and then your y stays the same. Okay, so 6, 6 is going to become negative 6, 6. Right, and this would be K prime. Okay, and if you want to do the other ones, right, H is 3, 2. It's going to become negative 3, 2. And there's H prime. Okay, J here is 6, 2. It's going to become negative 6, 2. And there would be your reflection over the y-axis. Okay, use the graph below. What is the rule for translating point A to point D? So translating A to D. So we're going 1, 2, 3, 4 to the right. So that's plus 4x plus 4. And then we're going down 1. So that's going to be y minus 1. So we're looking for x plus 4, y minus 1. We're going from A to D. So we're going right 4 and then down 1. Okay. All right, segment CD was dilated around the origin by a scale factor of 2. So we're not doing dilation, so let's not worry about this one. Okay. Point X, -3, -2, is translating using the rule xy goes to x plus 3, y plus 3, then over the x-axis. So we want to know the coordinates of x double prime. So let's first find the coordinates of x prime. Okay, so x is the point -3, -2. So here's x, -3, -2. Okay, so if we're going to go 3 to the right, right, x prime, right, we're at -3, so -3 plus 3 is 0. Okay, -2 plus 4 is 2. Right, so we're at -3, -2. If we go 3 to the right, we're going to be at 0. And if we go up 4, we're going to be at positive 2. So here's going to be x prime. It's going to be 0, positive 2. Okay. And then we want to reflect over the x-axis. So if we reflect over the x-axis, we're going to be at 0, 2. So x double prime will be 0, -2. Right? When we reflect over the x-axis, we're changing the value of the sign of the y. Right? When you reflect over the x-axis, you're reflecting up and down. So your x value stays the same and your y value changes sign. Right? So x prime is 0, 2, so that means x double prime is going to be 0, -2. Okay, so 0, -2 is option B here. All right, and the last one here, a rectangle is plotted on the coordinate below. Okay, and there's not really a question for us here. Basically, it's to say what sort of rotation or translation or reflection did we do here. Okay, so for the first one here, right, here's your original. Right, so this is a 90-degree rotation. 90-degree rotation. Clockwise. Okay, you could have also say 270, right? Or 270 counter clockwise. Right, so we could make a better or here. Right, so this is a 90-degree rotation clockwise, or you could say 270 degrees counterclockwise. Okay, this one here, again, here's the original. So this one is a 180-degree rotation either way, whichever way you do it. So it's going to be a 180-degree rotation. Okay, this one here, right? This is a reflection over the y-axis, so reflection. Right, and then this one's a reflection over the x-axis. So this one is reflection right? This one we're rotating 90 degrees. This one we're rotating 180. This one we're reflecting it left and right, so reflecting over the y-axis. And this one's a reflection over the x-axis. Okay, and that's it for the in-class review.